Hello everyone. We were working on these a bit dark on these solutions using power series, but although this is in the same chapter, we will do now something where we won't use power series, and in fact we won't use power series anymore. The next chapter will be about something else again. So, but why is this linked to what we see previously? So I remind you, we were looking at special types of linear second order equations, and were always homogeneous. And what was special was that the A, B, and C were polynomials. So these are all polynomials. And so far we have been dealing with a case that we looked for a solution that was centered, a power series solution that was centered at some, so we had a power series solution, something like this, such that A of x0 was not 0. Okay, we call this an ordinary point for the differential equation. So what happens now if we are in a case where x0 is a root of this equation? So a singular point, x0 is a point where the coefficient in front of I double prime becomes 0, and that causes problems for definability somehow at around x0. Okay, so these are singular points, and there's even distinction in between them. There are regular single points, so and irregular ones. So regular, singular points, and there's irregular singular points. And what is it to do is how many times is this a root? Okay, regular single point means that x0 is a root of multiplicity 2 and a root of multiplicity of A and a root, doesn't matter what the multiplicity is, of B. So there are two conditions. It has to be a root of multiplicity 2. Remember, that means that you can factor out x minus x2 squared, but not more. That's the multiplicity 2. And here, to be a root of this one means that you can factor out at least x minus x0. So this looks something like this. So this looks like x minus x0 squared, and then the rest, I'm going to call that again ax. Or let me call it px now if you don't want to get confused, plus x minus x0 qx plus rx. Let's use different letters. Rx, sorry, there's a y. The y, I forgot my y's here, right? Okay. Oh, here I also forgot my y. Okay. So I'm talking about this coefficient. So you see what this means is that we can factor out a factor 2 here, but what does it mean that you cannot factor out more? It means that this is no longer 0 if you plug in x0, and p of x0 is not 0. Okay, it cannot be x minus q cubed that you can factor out. If this would be 0, then you can factor out another x minus x0, so that's not allowed. Okay, but here you can. That doesn't say that you cannot here do it, but it has to be at least once. Okay. That's a regular single point, and otherwise it's called irregular. So, for instance, here is a system of differential equation, and let's introduce already what the main topic, an Euler equation. It's an equation of form ax squared y double prime plus bx y prime plus c equals 0. So this is a very, very special case of a regular singular point. So x is 0. Of course, this is now it's 0, right? x0. Let me know. Yeah. X is 0 is a regular singular point. because we have x squared here, sorry, and there's an x squared here, and this is no longer, x equals 0 is no longer a root, it's in fact a constant here. So in the general definition, this doesn't have to be a constant, okay? This has a factor x that can factor out, and in the general definition, this could be any polynomial. And this could also be any polynomial. But here we have a, b, and c are constants. So the Euler equation is a very special equation where we have constants. So it's not a constant coefficient because there's x squared and x here. Okay? But it's very similar to that. Okay? So, all right. So an example, just one example of something an irregular. So these are regular singular points. So here's an irregular one. Would be x cubed y double prime plus x y prime plus x y equals 0. Why is this? Make me this x squared, and let's call this. Perhaps let's call this just. Sorry, let's look at this. And I'm claiming that x is 0 is an irregular singular point. Why is that? Is it because we have an x squared here? No, it doesn't matter. Here you can have any power of x. It has to be at least 1. But here, the power is too high. Okay, and that's why it's not of that form. Now, all this is not important because what we will look at is really just these guys here. Euler equations. So for the rest of the chapter, we're just going to do with that, and we're going to look at a special method of solving them. And so how to solve. This was just an introduction, but as I said, you can safely forget a little bit all these definitions. We won't use them anymore about irregular, regular singular point. It's just that you know that we're dealing here with a very simple case of regular singular point, Euler equation. So right, again is ax squared y double prime plus bx y prime plus cy equals 0. Okay, so the first step that we have to do, step 1, of course it's homogeneous, right? So there's no splitting in homogeneous and non-homogeneous. If this would have been constant coefficients, in other words, if this power of x were not there, then we would look at the characteristic equation. We now look at something which is almost the same. So it's a little bit dangerous to get confused here. This is called the indicial equation. And so, remember the characteristic equation, let me first have the characteristic equation. This looks like this. A_t squared plus bt plus c equals 0, right? But what's the difference? This part here is not a t squared, but it's a t times t minus 1. So, t squared would be t times t, right? And here is t times t minus 1. Okay? This is called a difference. Polynomial instead of a regular polynomial, but that's not important here. So this is the only little difference. Okay, so it's simplest to memorize it this way. Although of course you in practice when you're going to work with it, you're going to expand this. So notice that if you expand this, it was et squared minus at plus bt plus c. So there will be et squared plus b minus a. T plus c equals 0. So that actually will be the actual equation that we will solve. But it is easier to write it down this way. So let me box it because we're going to use it all the time. Because then it's easier to copy, to write it down from the Euler equation. So notice that the x's have not been copied, right? It's only the constants that we copy. Okay. So what do we do now? So there again, what was the situation in the characteristic equation? In the characteristic equation, we had 3 possibilities. We had the discriminant was positive, we had the discriminant was 0, and we had the discriminant was less than 0. Professor, what was this discriminant again? Well, this meant that there was 2 real solutions. This meant that there was 1 singular, so one real solution, counted twice, with multiplicity 2, we have used that word before now, multiplicity 2, meaning this equation factors as x minus something squared, okay? And the discriminant less than 0 means that two conjugate complex numbers, complex solutions, okay? So let's give them names. So R1 and R2. These are the two different ones. If there is one, we just call it R. And if they're two complex, then we will call them lambda plus minus I, or omega I. Remember, that's kind of almost the same than in the previous cases. And so how does it now put together? Okay, so here is now the solutions. The general solution. How does it look like? Well, instead of exponentials with these R1s, this will become now powers with that as exponent. XR1 and XR2. Okay? And okay, so we'll have two coefficients, C1 and C2. So x to the power R1 and x to the power R2 will be a fundamental system of equations. Now, what are these r's going to be? They're going to be, in general, real numbers. They could also be negative. So they could also be rational. So we have to be a little bit careful what values of x we plug in. For instance, if this power would be a half, then we cannot plug in a negative number. So to avoid all this, we really, again, we didn't pay much attention to the where these solutions are defined. But so if you don't want to run in any problems, just think for x positive. Okay, for x positive you can do this. Even if this is a real number like pi. It sounds weird, but it's definable. You can define this. Okay, so what happens in this case? Well, of course, you would say the same xr and xr, right? Now, that's where it goes different. And what did we do the other time? Professor, I know. You multiply this with x times xr. No, because that if so, you would think x times xr, right? Not this. Well, what would that be? That's just that. So this would fall in the previous category, but that means that r plus 1 would be a root. No, r plus 1 is not a root. We have only one root. So this cannot be a solution. And so it will be perhaps a little bit surprising that we're going to multiply not with x, but with ln x. So xr ln x. Okay. And then the last one, what is that? Well, we know that the complex numbers, then we know that this will be a frequency, so we have cosine omega x, and we have a sine omega x. And we also know that there was this lambda here in the constant coefficients. This would have become e to the lambda x. But again, instead of exponentials, we now powers. So this becomes x to the power lambda. And x to the power lambda. And again, we have a C1 or an A here and a B. Let's call it A and B. Okay. So the situation is almost the same, except that instead of exponentials, we have powers. Okay. And therefore, instead of x, so if you want, it's instead of, look, I don't want to make the analogy too much, but so if you have ERX, okay, so we now have x. This is the same as EX to the power R, right? No, let me not, I don't want to say this. It's going to confuse me more than it helps you. Okay, it's just similar but not the same. Sorry, here of course an A plus a B again, okay? So the fundamental system of equations are different in the three cases as it was for constant coefficients, but it's just a different setup. So let's practice this. Okay, here is the first one. X squared y double prime minus 5xy prime plus 9y equals 0. So step 1 is the initial polynomial or equation. That would be, so we drop the axis, and it would be t times t minus 1. That's how you replace y double prime. Minus 5t plus 9 equals 0. So for the lower powers, for the lower ones, it's the same. It's just the top one, instead of a t squared, goes t times t minus 1. So I have to expand this as t squared minus t minus 5t plus 9. So that is t squared minus 6t plus 9. Okay. So what does this look like? Okay, we have to factor this, right? This is t, two numbers that multiply to 9 and add up to negative 6. That's minus 3 and minus 3, right? You could also have immediately recognized this was the double product. So what situation are we in here? So we are in this situation, right? So this situation here. And so we know what the solution look like. The solution look like, so step 2, the general solution is y equals a times x to the power 3, because r is 3, plus b times x to the power 3 ln x. Okay. Now, if we would give initial conditions, we cannot give them at 0. Why not? Because the function, that's the whole point. 0 is an irregular, is a regular singular point. It's a singular point. And so the function would not be defined at singular points. Remember, that's because of this. If you think of this somehow, if you want to get rid of this coefficient here, then you have to divide everything by x squared, so you get the denominators. In the denominator, you get an x, and that x in the denominator will mean that it cannot define. It's not defined at x equals 0. So an initial condition. So let's impose initial conditions here. There would be something of the form. So I'm adding this now, right? So y1 equals 3 and y prime 1 equals 5. I don't know what it does, so let's do this now. So if x is 1, then y is, what did I say, 3, and y prime is 5. Okay, so these two we can plug in, and we see that 3 is equal to a 1 to the power 3 plus b 1 to the power 3 ln of 1. Oh, that is 0. So a is 3. Oh, okay, that was quick. We also need y prime. Okay, that is 3ax squared plus, now we have a, be careful, double product formula. So we have 3bx squared ln x plus, copy the first, take derivative of the second, bx cubed divided by the derivative of ln x is x, right? So it's this one. Now if I plug in 1, then the ln part goes again, and so we get 5 equals, so I'm plugging these two things in now, right? 5 equals 3a 1 squared. Any power of 1 is 1, right? So even here, what is this? Okay, we can simplify this, right? This is bx squared. Let's do this. So plus bx squared. Okay, you see where it comes from, right? But it doesn't really matter, because if I plug in 1, it's 1. So plus b. So and a was 3, so we get 5 is 9a plus b. But it's 9. Okay, it's 3. So b is negative 4. Okay, and so our solution was y equals 3x cubed minus 4x cubed ln x. Okay, so that's an example. Let's do another one. I want to do something that you see everything going on. So let's do 6x squared y double prime plus 5xy prime minus y is 0, and let's do the initial conditions. Y1 is 3 and y prime 1 is 4. Let's see, I'm not sure whether it will give nice numbers. If not, then I might change the number a little bit to get it nice. Okay, so step 1, the initial, don't say initial, right? Initial, from, it's, if you want to know what's the root of this word, this comes from index. Initial, the one that makes the index. Why is that called that way? That's beyond the scope of what I'm doing here. But so initial equation is 6t times t minus 1 plus 5t minus 1 equals 0. So that's 6t squared minus 6t plus 5t minus 1 equals 0. So we get 6t squared minus t minus 1. Okay, is 0. So, okay, we're going to use the AC method to factor this, or we can do quadratic what are the formula, right? So we need two numbers that multiply, so AC is equal to minus 6 and B is equal to minus 1. So two numbers that multiply to negative 6 and add up to, multiply to negative 1, what is it? Multiply to negative 6 and add up to negative 1, sorry, I said it wrong. So let's see, something with 2 and 3, right? So minus 3 plus 2, that is minus 1, and minus 3 times 2, that is minus 6, okay. Remember, the next step, there's one more step that you have to do. You write now this minus 1 as minus 3 plus 2. So you get 6t squared minus 3t plus 2t minus 1 equals 0. You might ask, is there a particular order? Should I not have written this as 2 minus 3? No, it doesn't matter. It always will work. So, okay, now we group together. Here we can factor out the 3t, and we get 2t minus 1 left. Here we have just 2t minus 1. So I can factor out the 2t minus 1, and what is left is a 3t plus 1. Okay, so we see that the two roots are 2t equals 1, so t is a half, and this is 3t equals minus 1, so t is minus 1/3. Okay, so what our case are we in? We are in this case, where we have two real solutions, and so it will be the two powers that we will get. So in this case, so the general solution, so step 2, the solution is y equals a times e to the, not e, see, I'm so used to thinking about the previous one, it's x to the power half plus b x to the power minus 1/3. Of course, that is, you could write this as, so if you want to write this is a radical x plus b over cube root of x. If you want to understand what these powers are, so you see that's where these powers can be. These functions can be different. It's not just you don't think of this x to the power r just as r squared, x squared, or x third or something like that. This could be like irrational powers. Okay. All right. So this is the general solution. And so let's now again look at the initial conditions. So if x is 1, then y was, what did I say, 3, and y prime was 4. So these two plugged in, it gives me 3. 3 is, and again, whatever this power is, any power of 1 is 1. Any negative square root, whatever it is, 0, it's always 1. So 3 is equal to a plus b. Okay, we also need y prime, but that's again the power rule. So y prime, I'll do it here, y prime is half a x to the minus a half minus 1/3 b x to the minus 4/3. Okay, subtract 1 from the exponent. So if I plug in now 4 at one side and 1 at the other side, I get a half a minus 1/3 b. Again, it doesn't matter what these powers are, if I plug in 1, it's always 1. So the last one, we should perhaps clear the denominators by multiply everything with 6. So 6 here, 6 here, and 6 here, right? So I get 24 equals 3a minus 2b, and we also had 3 equals a plus b. So we can either do substitution or we can do elimination. Let's do times 2 and add this up to that. So what we get is times 2, 6 plus 24 is 30, equals 3a plus 2a is 5a, and 2b minus 2b is 0, so we get that a is 6. And once we know that a is 6, we can plug this in here, and we see 3 is 6 plus b, so we see that b is negative 3. Sorry, 2 negatives there. So our solution is 6 square root of x minus 3, square root of x. I say square root of x and I write it in the denominator. 6 square root of x minus 3 over the cube root of x. That's being fancy, but if you don't want to be fancy, you can just write these powers here, okay? That's fine. All right, so we kind of almost saw everything, right? So let's do one more. Oops. X squared y double prime minus 5xy prime plus 9y equals 0. Okay, the initial equation, that's step 1, right? That would be t times t minus 1, there's no coefficient, minus, well, 1, minus 5t plus 9 equals 0. So we get t squared minus 5t plus 9 equals 0. Oh, no, that's not the one. Sorry, I copied the wrong one. That was the one we just did, right? Before. Right. I copied the wrong one. Sorry about that. We did that, so I don't want to do that again. The one I want to do is this one. X squared y double prime plus 3xy prime plus 2y equals 0. So this would be t times t minus 1 plus 3t plus 2. Now be careful, right? You say, oh, two numbers that multiply to 2 and add up to 3. No. We have to factor this, expand this first. That's a t squared minus t plus 3t, that becomes 2t plus 2 equals 0. Okay, and this is not factorable. In fact, it's complex root, so we can do the quadratic equation, but you can also do the completing the square. Just for the fun of it, I'll do the completing the square. See, I have to complete the square here. What is missing? Well, there's only one thing missing here. I need a plus 1. Okay. Now, first of all, I have to make this equal to this one here, so I have to add another one to make it equal to 2. Okay, so this now becomes t plus 1 squared plus 1 is equal to 0. So we get t plus 1 squared is equal to negative 1. And so we find that t plus 1 is plus or minus I, the square root of that. And so t is equal to minus 1 plus or minus I. Now, that's completing the square. Because it was rather easy here, that's why I wanted to show you. But of course you can also do the quadratic formula. So if you do the quadratic formula, that would be minus 2 plus me on the square root of b squared, that's 4 minus 8 divided by 2. And you see that this will come down to the same. Okay, so what does this mean? This is lambda is negative 1. And what is omega here? Not I, right? Omega is the coefficient in front of I, the imaginary part, and this is 1. So we know that the general solution, so step 2, the general solution looks like, what do we do with this negative 1? That will become the exponent of x. And then here we get this regular thing, the cosine omega plus b sine omega. Sorry, I'm saying it wrong, right? I meant to write x here. Wait, let's fix this. Okay, let me write it over. So omega is 1, so it's a cosine omega x, so x, plus b sine x. Okay, and that's the general solution. Oh, sorry. I gave you the wrong formula, I realize now. I gave you the wrong formula in the last one. I said this is, sorry. Remember, it's not x's that we have to, instead of exponentials we go powers, instead of x we go ln x. So I give you the wrong formula here. This is just the wrong formula. It is a x r, that is, but then here we get sine or cosine omega, not x, ln x, plus b xr cosine omega ln x. I'm sorry about that. That was an oversight of me. I copied it wrong. So that's what I was confused here. I was expecting an ln and didn't have it anymore. Okay, so this is a cosine omega is 1 of ln x plus b sine of ln x. Okay, and so now we can again do an initial condition. I didn't write one, but let me add one to it. Say again, if x is 1, x is 1 is easy here. So y is, I don't know, 3 and y prime is 4. So x is 1, y is 3, y prime is 4. So if I plug this in, the first two I can plug in, right? Again, any power of x is x, so this 3 is 1 times A, the cosine of ln x. The ln x is ln of 1 is 0, so the cosine of 0 is 1. The sine of 0 is 0, so a1 plus b is 0. Remember, ln of 1 is 0, right? So this means that a is 3. We also need to take derivatives, and that gets a little bit messier because for one thing there's a product, so we get minus x to the minus 2, that's the power rule, and then we copy that guy, cosine ln x plus b sine ln x, plus now we copy the first factor and take derivative of the second one, but that's an inside function. So that is, derivative of cosine is minus sine, so get minus a sine, plug in the inside function, and then multiply with the derivative of the inside function. Plus, derivative of sine is cosine, so b cosine, plug in the inside function, times the derivative of the inside function, 1 over x. So you see the derivative is getting already quite ugly. But luckily, this is y prime. If I plug in x is 1, y prime is 4, we get 4 equals, again, powers, we don't care. ln is 0, so we have a times cosine 0, okay, so that is a, right, a times 1. The sine, again, is not there. So the sines are not there, so it's a cosine, right? So in this, this term will survive. Again, all this gives me ones. This is 0, cosine 0 is 1, so I get just b. A plus b. So you see, these initial conditions become rather simple in this case. So, and we know that a was 3, so 3 plus b, so we see that b is 1. So our solution is, this for these initial conditions, was a was the one that went with the cosine. So it's 1 over x to the power negative 1, times 3 cosine ln x plus sine ln x, because b was 1, and this is our solution. Okay, so this is actually rather simple, right? It is just one formula, and then you have 3 different cases, and then you have initial conditions. Unfortunately, in the homeworks, they do not ask any initial condition problems, so you could put some for yourself, or they're not hard. But on the quiz or so, I might add some initial conditions. But you see, they're really not difficult. Especially, well, they're not difficult if I do x equals 1, because then the ln is 0 and so on. It becomes easy. Okay, all right, that was it.